Okay, so the topic of the lecture is atom probe tomography, principal techniques and applications. So first we're going to look into the fundamentals, just explaining what it is, what it does, and how it works. Then we're going to look a little bit into instrumentation, experiments, and data analysis. So these are essentially going to be the 4 lectures. And then we're going to do the practicals, because it's, well, circle of people is small enough, so we can certainly do that. Yeah. Okay, so atom probe tomography. What is atom probe tomography? Well, it's more or less the answer to how to analyze single atoms in solid materials. And so what we work on typically is a couple of different things. So we work on interfaces. That's very regular, something that we do. In this case here, we see a grain boundary, and you can see carbon atoms at a grain boundary. We also very often work on clusters. So here we see very small magnesium copper clusters in aluminium, which is also something that interests us here because we're working on aluminium alloys. Precipitation is a very, very regular field as well. And in precipitation, here we're working especially on superalloys, but also on aluminium alloys. So clustering and precipitation is just, this is just very small clusters, and this is larger foreign phases. And for the small clusters, there's really no other way to really find if they exist or where they are and so on. And this is why we use atom probe for this. We can also deduce some structure. Very importantly, so sometimes we can use the image that we get to figure out what the crystal orientations are, and I hope you're going to see in a couple of slides how that might work. And if I get the 3D printer to properly work, I'll make some models so that you can see that that also makes sense if you just look at it from a very simplistic perspective. And very importantly, what we very often do is we try to get composition. And the basic principle is that we have a tip, that we have some kind of tip that is on a nanoscale, so that the individual atoms really become visible. But that's got something to do with the amount of field that we need. So we need a lot of field. And essentially we need so much field that individual atoms get ionized, and then they depart from the surface, and we direct them towards a detector, towards some kind of detector. And we typically ionize the specimen, that's atom probe, but we can also add a gas and ionize the gas, then it's field ion microscopy. This is why these two things are relatively close to each other. Very often you can do it in the same instrument, not in the modern instruments, but back in the days, that's usually what you did. Because the atoms leave the surface, the specimen gets shorter and shorter and shorter, and this gives us a tomography aspect, because an atom here might fly towards here, an atom here might fly towards here. So we get lateral resolution, we get depth resolution because we make the specimen shorter. Of course, this hinges on the whole thing being a relatively controlled process, which very often it is, especially in pure metals or alloys. But if we look into materials where this is where we have a lot of different phases with very different atomic bonding, it might not be that controlled in effect. But this is what everything hinges on, essentially. And in order to be able to get the composition, what we do is we pulse the field in time. So typically here we have a positive voltage, and here we have typically ground or a negative voltage in order to get the high electric field that removes the atoms. And they would come off at random times if we don't additionally provide some pulsing, which can be a voltage pulse, so that voltage over time varies, or we can vary temperature over time, same effect. so that we know that the field evaporation probability is high only in a very short period of time, so that we can measure what the arrival time at the detector is, and from this we get the time of flight and the mass to charge ratio. That's the basic principle. For all of that to work, we obviously need to be at a very low pressure, so 10 to the minus 9 millibar or better. And we need it to be at low temperatures. The temperatures are typically below 60 Kelvin. Sometimes we can work at higher temperatures, but typically we're below 60 Kelvin. And most modern machines can go down to 20 Kelvin, like our two machines that we have. People have recently done also research of going to below 20 Kelvin, but then we don't see many advantages anymore. But we'll talk about that later. But this is sort of the boundary condition, and this sort of sets what kind of instrumentation we need, because we need the cooling, we need the temperature, we need the high voltages, and we need a laser. And during the period of this lecture, we're also going to get a new laser for one of our machines. So you're also going to see how a new laser gets installed on an atom probe, and maybe we'll do a little bit of a demo and show you how that works. Okay, so let's go through the fundamentals and research areas. So typical research areas are, of course, metallurgy. This is what we do a lot, and this is where everything started. And you'll see why when we get to specimen preparation, because very often metallurgical specimens are relatively easy to make. And of course, they're electrically conductive, because remember, we're using high voltages and pulsed voltages. Just a static high voltage wouldn't be a problem with a ceramic, but because it's pulsed, we need electrically conductive specimens if we do voltage pulsing. It's laser pulsing, yes, this is voltage, but we can do laser. Ceramics is laser only. There's no way you can do ceramics without a laser, because in this case electrical conductivity is very low. Nanomaterials, voltage or laser, but typically the laser also puts smaller stresses on our specimen, so if we have a complex specimen, very often we also use laser. Semiconductors is also laser only, same reason, bad conductivity. So here we got voltage or laser. And then we've got more modern things, like recently people have started doing measurements on water, where the water ice is frozen, and then you can look into the distribution of species in water. And this is, for example, really good if you want to do chemistry. So if you think about chemistry, very often if you go into chemical lectures, what you see is very nice computer models of where stuff is, but nobody has ever seen it. And this sort of gives us a chance in the future to maybe even freeze in chemical reactions, look how they're distributed, which species occur, and so on. But this is really in its infancy. This is not something we're doing here, but it's something we could do here. So we have all the equipment to do that. We just haven't had the research drive to do it because we've got a lot of other things. Geology, same thing, non-conductive specimens, so laser only. This is also something we do here with collaborators. So we've already published close to half a dozen papers where we look into geological samples, where the important thing is that since we measure the mass to charge ratio, we'll get to why mass to charge ratio. Since we measure the mass to charge ratio of ions, we can also very often say what their isotopic nature is, which is really great for geology. Because isotopes is something geologists love, and trace elements is something geologists love, and this works well with atom probe. And you can already see, if you look at the page now, how often you see laser and how often you see voltage. So laser really has been greatly expanding the application area for atom probe tomography. And even in areas where voltage measurements are possible, voltage pulsed measurements are possible, we very often use lasers to increase specimen survivability, increase the amount of ions we collect before a specimen breaks, because the high voltage also produces a high mechanical stress in our specimen. Okay, so where is atom probe tomography positioned? So the important thing about atom probe tomography is really that we're working at a very high spatial resolution at the nanometer scale, and we work with very good detection sensitivity. Because remember, we are removing individual atoms, so we are counting atoms. As a result, the method is inherently quantitative. Let me just check if our guest can hear us. If you can hear us, just write something in the chat. Okay, let's assume he can hear us. Okay. Since we're counting atoms, we're inherently quantitative. The detector, we'll get to detector technology next time. The detection has a very, very low background. And as a result, we have very high sensitivity. So essentially, the sensitivity is more or less limited. The sensitivity is more or less limited by the detection count of the atoms. Yeah? So if we take a measurement, typically our results are somewhere, usually we're collecting somewhere between 1 million and 100 million atoms would be typically a typical atom probe data size. So what kind of analytical sensitivity would you expect then? Say you've collected 10 million atoms. So if you're trying to measure 1 ppm, how many atoms would that be? So if you collected 10 million atoms, how many atoms of 10 million atoms is 1 ppm? No, 10. 10. It's 10 atoms, yeah. So you're counting 10 atoms if you want to see 1 ppm in a 10 million atom data set, which is kind of possible. Yeah? It's kind of possible. And this is why it says unphysical region here, because if you collect very small volumes, then you can't go to very small concentrations just simply because they make no sense. Yeah, because you would say, do I have quarter of an atom in my data? That doesn't make any sense. Yeah. And this is essentially where atom probe is positioned. So we're at a very high analytical resolution, typically in the range of 1 or 2 nanometers, and in some cases where the field evaporation is very well behaved, it can get better than that. Yeah? But typically it's in the range of 1 to 2 nanometers, roughly. In depth, typically it's much better than that because we're looking at the evaporation sequence. But laterally, we can have some deviations in the ion trajectories. We're going to discuss that later on. That lead to lower lateral resolution. And you can see we're in regions where there is no other analytical technique that really exists. Which is on one hand great because it's a use case for the instrument, but also on the other hand you have no way to cross-verify your results because there is no alternative technique that you can use to cross-check. Sometimes you can use analytical electron microscopy, which can reach similar spatial resolutions, but not analytical sensitivity and accuracy. Or otherwise you need to go to atomistic simulations. And we, for example, we have published some work where we've used atomistic simulations to sort of verify what's happening. But there is no experimental technique really that can give you comparable results. Okay, the whole thing was also not a new invention. But really it started in the 1950s. The origins trace back to the 1930s really, but it started in the 1950s with field ion microscopy, and we're going to have a look into that shortly, and with electropolished specimen preparation. Because remember, we need a very, very sharp specimen with a tip radius of, let's say, 50 nanometers or something, or let's say 10 to 100 nanometers roughly. And the question is, how do you make that? And essentially, you can even make it at home in your kitchen. If you take the wire from an old light bulb and some drain cleaner, and if you have a toy railway, you can use the power supply from that to do some electropolishing and make an atomically sharp tip. And this is actually a very powerful technique. And for example, scanning tunneling microscopy, the tips for scanning tunneling microscopy are also made exactly that way. It's a very, very low-tech technique for materials where you can use let's say, nice chemicals, some of the nicer chemicals like KOH and NaOH, which works, for example, for molybdenum or tungsten. Here we very often work on aluminium or nickel-based superalloys or steels. In this case, we need hydrochloric acid for electropolishing, which is a relatively dangerous acid because it's explosive. This is not something you can do at home. But it's perfectly possible in a lab, and we do that here pretty regularly. And in the 1950s, we'll get to that, they made the first field ion microscopy images. So these were exactly the first images where people were able to see atoms. And we'll get into Erwin Müller and how he did that. And what they also observed is that during the experiments, they could see individual atoms departing the surface. So at the time already, the question came up, can he do something with that? Can he possibly capture those atoms and analyze what they are? Of course, in this case, this is a tungsten specimen. You'll see that very often because it's very easy to do in field ion microscopy. It's not that interesting because you know each atom is a tungsten atom. So why would you analyze them? They're all tungsten. But as soon as you start having things like, in this case, a grain boundary, and if you're a professional atom prober, you already see that here there's some kind of defect, essentially a grain boundary. So probably all of you know what a coincidence site lattice is, right, from your basic crystallography lectures. And that was discovered exactly like that. So when people looked at in field ion microscopy at grain boundaries for the first time, they noticed that they look the same, after every however many atomic distances between them. And this gave rise, this was the idea behind the coincident site lattice. They say, okay, if I have two lattices like a Moir pattern, they will have repeat units to them as well, and this is exactly what you see here. Okay, and so with the advance of detector techniques in the late 60s, in 68 to be more precise, the first atom probe field ion microscope was built, so the atom probe part came in, and the atom probe part is essentially the catching of the atoms. So one of the PhD students at Penn State had the idea to use time of flight mass spectrometry, and so what they did was pulse the field with a voltage pulse. Again, this was at the time when lasers had been invented, and the pulse periods in lasers were relatively, the pulse durations were relatively long. The first lasers we see in the 80s. And from that, they just got time of flight data. So they didn't know where on the specimen that the atom came from. But if you use a small aperture, you could just localize it to, it says here propole. So they, for example, would put an aperture exactly here so that they knew they were somewhere near the grain boundary. And then they could evaporate individual atoms and analyze them by their time of flight. At the time, everything analog, so it was an oscilloscope to analyze. And this gave you the time of flights, and from the time of flights they then look at what elements they are. And here is it tantalum, tantalum hydride, tantalum helium hydride, tantalum helium H2. Yeah. And this is important to bear in mind, because very often if you try to do the experiment, people will look into old papers and just use the experimental conditions from back then. But depending on what instrument you're on, they might have a very different meaning. Yeah? So very often one setting that we use is a so-called detection rate, yeah? which just says how many atoms do we detect in each pulse. Yeah? And typically we detect 1 ion every 100 pulses, roughly. This is a setting. Yeah? I could set it to detecting 1 ion in each pulse, or 10 ions in each pulse. Yeah? But typically, you'll hopefully know after we look at detector technology, typically we use 1 every 100 pulses, as we can really make sure that we isolate them and really find out which atom is which. But of course, if you only take a very small section of your specimen and you detect 1 ion every 100 pulses, and all of the atoms around it get lost in the detection system, of course you evaporate your specimen much faster than when you have a detector that covers the entire specimen and you detect 1 atom every 100 pulses. Yeah? This is always something that's very important and people forget very often these days. Yep.
And the time is then too long if we did just 1 per 100 pulses, 100,000 pulses, because we have to do it so many times for each atom, each ion.
Yes, so the fewer atoms you detect, the longer your experiment takes, and this is a trade-off. But we'll get into how fast we can pulse and how fast we can measure with the instrumentation. But typically we pulse these days, we pulse with several hundred kilohertz. So our systems, both the voltage pulses run at 200 kilohertz. So if you detect an atom every 100 pulses, you detect roughly 2,000 atoms per second. So you do get a pretty good speed. And I actually wanted to buy a pulsar with 500 kilohertz or 1 megahertz. But the problem was that then Russia attacked Ukraine, and the people that built my nice pulsars live in St. Petersburg, so I'm not allowed to buy anything from them anymore. So that's why we're stuck with 200 kilohertz for now. And eventually, if you get much faster than that, we can have a look later in what the flight times are, because of course you want the next pulse only to come once all of the atoms from the previous pulse would have arrived, all the possible atoms from the previous pulse would have arrived at the detector. And typical flight times are in the microsecond range, 1, 2, 3 microseconds. So 1 megahertz, you can only work with light elements because heavier elements would take longer to fly. But we'll see that later on.
What the processing time of the detector?
That doesn't actually matter, but we will see that later on, because the detector processes in sequence. Okay, and then of course people thought, okay, it would be nice if I could see where the atoms come from and what they are. Not just either where they are or what they are, but I want to see what they are and where they are. And there were 2 stages to that. One in the late 70s, which was the so-called imaging atom probe, where the detector, essentially the same detector that was used for field ion microscopy, was used, but was only switched on for a very short amount of time. So essentially, they were switching it on only for the time when a certain species would arrive. In this case here, it's oxygen, oxygen in molybdenum. Oxygen in molybdenum. And this, for example, how it was discovered what leads to the embrittlement of oxygen and molybdenum and tungsten. But in this case, you can see where certain ions are, but you have to know beforehand what you're looking for. And then you can only see that one type. So if I wanted to see at the same time where other stuff is, then I cannot see it for the same section, because the detector is only on for a very short amount of time. So in the mid 80s to late 80s, the first 3D atom probes came into play. So essentially in the early 90s was what we now see as a tomographic atom probe, and before that there was a position-sensitive atom probe. A position-sensitive atom probe, the 3D aspect wasn't as widely used. And essentially what that was the our friends in Oxford, which is now, the group is now headed by one of my former office mates. What they did was they bought a detector from astrophysics and used that one because that one had a time resolution and a spatial resolution. But the spatial resolution wasn't all that great, and it didn't have a lot of capacity for two atoms coming at the same time. It was a so-called wedge and strip detector. And the first real tomographic atom probe came out of France, out of Rouen in the early 90s, early to mid 90s. And they had a so-called multi-anode array detector, and that was a much more capable detector. And this is the results that you see here. And in this case, they could detect the flight time and the position simultaneously. So in this case, it was the position-sensitive atom probe in Oxford and a tomographic atom probe in Rouen. And this is actually already the basis for everything that we have now, except for the lasers. So the first lasers were used in the early 80s, but they were nanosecond lasers. So the spatial resolution was washed out by the laser, and they only came back in the 2000s. And from there on, the development went to better setups, better experimental setups, and larger detectors. And using delay line detectors, which is what all current atom probes are using, delay line detectors. And we'll look into that in detail. And in the early 2000s, modern lasers came into play. Essentially picosecond and femtosecond lasers. So picosecond and femtosecond lasers came into play. And then further developments going to shorter wavelengths and so on. And so most of the modern setups that you see are from 2010 onwards. Which are the sort of really good commercial laser setups, wide field of view, and now we're seeing continuous development on this for even higher field of views, more modern lasers, and so on. So this was one aspect. All of that you can apply even on the most basic specimen you could have made in 1930 already. But what interests us these days, because we can work with non-conductive specimens, is, of course, a lot of those specimens, and you cannot electropolish them. Electropolishing only works for metallic specimens where the feature that you want to look at is going to be in your specimen anyway. Precipitation is a very good example, because precipitation is more or less the same everywhere. But grain boundaries, already a problem. How do you work on grain boundaries? Here you can see a grain boundary. So how did they get the grain boundary there? Well, you can use nanocrystalline materials, then you have grain boundaries everywhere as well. But if you want to go in a regular material and take out a grain boundary, you need some technique for that. Back in the days, people had very sophisticated ways of doing that with electropolishing and transmission electron microscopy, but very often it was an entire PhD thesis for 2 or 3 data sets, because there was a lot of work. So what then came about was ion beam-based preparation methods. So in the 80s, we started seeing broad ion beams, because an ion beam will form a cone shape on a specimen anyway, just because of ion beam physics. There were some results from that, but very, very limited. But really the breakthrough of modern atom probe, just as much as the instrument development, is the specimen preparation with focused ion beam. And this is a very early example from, I think, Dave Larson from the late 90s, where they made the first specimens using focused ion beam. Additionally, then came focused ion beam lift out in the early 2000s, where also went into this the microstructure and said, okay, I want to pick out something from there and prepare the specimens. I myself was involved in quite some of the developments there, and nowadays this is pretty standard, that most groups that can do atom probe can go and do lift outs with the focused ion beam and prepare the specimens. One thing that's new here is that plasma fibs have also made it. So plasma fibs also allow us to essentially dig atom probe specimens straight into a flat substrate, so you don't no longer need to lift it out necessarily. And we have some developments on nanoparticles as well. So this light is already a couple of years old. At the time, this was sometime in the future. Now this is very much happening, and a lot of groups have plasma FIBs. What we don't have is energy discrimination in the detector, and we'll get into that. We also do not have 100% detection efficiency, and we also do not have new types of lasers available, but there is some research on that. And some of that research is actually done here by us. So you can talk to Merpat, my PhD student, for example. He uses ultra-short laser pulses for atom probe tomography, and this is one example. Okay, and so what is the basic question? Well, the basic question is how can we image or analyze atoms? And this means we need to have some kind of interaction with the atoms. And one interaction would be electron imaging. So this is early work from Albert Crew from the 1970s in Chicago, where you can see here, you've got two uranium atoms, and what he did was he did ultra-high voltage transmission electron microscopy, or mega electron volt transmission electron microscopy, built the first instruments that could show atoms, and the atoms were moving around because you bombarded them with very high energy electrons. And in the late 2000s, we started seeing things like evaporation corrected electron microscopy, where individual atoms or atomic columns can be addressed with a scanning beam, and then you can do spectrometry also on individual atomic columns. This is, by the way, also some connection to me. So this is David Muller's group, and David Muller actually learned a transmission electron microscopy on the same instrument as I did, because he's also a Sydney University graduate, and he was one of the first people to use the analytical electron microscope there, and I was one of the last ones because then it rained on it and it broke. So this is electronically, or you can have electron tunneling. This is also a way to interact with atoms individually. Very famously, Binning and Rohrer in the 80s got the Nobel Prize for it. So this is the original paper on silicon 7x7 reconstruction on silicon 1x111, where you scan over the surface and you see the lumps created by individual atoms. But the question is now, how can we analyze individual atoms? Because this is not possible in any of those configurations. Here, it's a little bit possible because the uranium atoms are sort of heavy atoms isolated on some carbon in this case, but here you couldn't analyze individual atoms, just atomic columns. Maybe these days you might work on 2D materials like boron nitride or some graphene. There you could look at individual atoms, and people have done that, but typically that's not the case. And the question is, how do you do that? Well, you need to be able to access individual atoms. And in order to be able to access them, you need to remove them individually. And this is what we do with field arm microscopy and atom probe tomography. And this is already something I showed above. This is the earliest examples from Müller and Badou in the 50s, where you can also see individual atoms bunching up here in individual atomic terraces. And some of the early work in the late 60s, where they used where they did the first spectrometry experiments. Okay, so how did that evolve? Well, it's all very much connected to a guy named Erwin Müller, who is from Berlin and did his early work in Berlin. And essentially at that point they had a bit of a challenge going on in their groups of how to visualize individual atoms. And some people thought, okay, let's do it with electrons. Let's build a microscope based on electrons, because they are the other criterion, because there we have particles, and we can use that for imaging. Remember, quantum mechanics was very new at the time. And Erwin Müller thought he's going to use field emission. Field electron emission at the time, because they were building the first field emission devices. And he built some of the first devices where he used very sharp tips to emit electrons and create an image from them, and what he got was roughly this. And he didn't see individual atoms. And at the time, they were wondering why that is, or they were just finding out why that is, because quantum mechanics was very new. And of course, nowadays we would know that the electrons, as they leave the surface, have a very low energy. So they have a very large delocalization in the range of 1 or 2 nanometers at that energy. And as a result, they do not possess sufficient localization to image individual atoms. So after the war, Mr. Müller moved to Penn State to the US to continue his work. And he thought, okay, if electrons don't work, maybe ions will work, because ions are much heavier. So the quantum mechanical wavelength is very, very short. And so what he did was build a field ion microscope with his students, just like we're going to build one in this course. And what they did was eventually they saw not a nice image like this one, but more an image like this one here. But they could see individual atoms. The reason why they didn't see a clear image like this one is because at the time they didn't have image intensifiers that are as good as ours that we have right now. We'll talk about them later on, so-called microchannel plates, so that they had to have very long exposure. So essentially you had to sit in a dark room for an hour to accommodate your eyes to the very faint image that you get before the image intensifier plates came. And the same if you want to take an image, it took very long to expose the image, and so everything got blurred out a little bit. These days, you can pretty easily just see it by looking at it, and some of the nicest images we have from our field ion microscope are just taken by our Hiwi Erik with his mobile phone. So very simple to do. It's very different for a field electron microscope, because the field electron currents are much higher than the field ion currents. So you don't need a lot of image intensification. But for the field ion microscope, you do need image intensification. And he also built the first atom probe in the late 60s. So you can see here, this is the basic setup. So here you've got the specimen at the end of a cryo shroud and some coolant, liquid hydrogen. And this was all made from quartz glass and pumped down here. And here you have the detector, which in this case is, I think, already a microchannel plate in this sketch. And we'll look into detector setups later. And as I said, you have some kind of aperture here, There's a field ion microscopy screen to aim, so you can move your specimen around, you can tilt it, so that you can find a certain spot on your specimen, and you have a probe hole in your film screen, just like you would have a hole somewhere in the middle here, so that you could aim. And then your ions can fly down the drift tube, and then you can analyze which ion is which. These style of atom probes obviously no longer, they weren't used for very long, mainly because you have a combination of high voltage, glass, and liquid hydrogen as a coolant was used at the time. And as you can imagine, safety-wise, that's not really a great combination. And that's why these days we don't have glass atom probes anymore. We have all of them are stainless steel, or in our case, titanium. And we use closed cycle helium cryostats instead of liquid hydrogen. But maybe in the near future we might have access to large amounts of liquid hydrogen, so maybe we'll use liquid hydrogen again. Okay, so how does the whole original setup work? So the original setup is very simple. So you have a glass bulb that you can pump out, evacuate. And eventually, if you have a closed system, because this is all glass blowing, so it did all of that via glass blowing. So you had a power supply to the specimen, which serves two purposes. Well, you could clean the specimen by heating it. We no longer really do that because we usually exchange specimens rather than refurbishing them. And you can apply the high voltage to a specimen. And then you just have a glass bulb with a phosphor screen. So phosphor screen, for example, you can look that up. It's typically these days a P47 phosphor. You can go and buy that, for example, and make your own screen. Of course, then without an image intensifier. And the rest is just a glass bulb that is pumped out, and that's really all there is to it. Then you can have either your ions emitting or you can have your electrons emitting. So this setup would be more useful probably for field electron emission and field ion emission. But this is how they all started, and this is why a lot of the early atom probe people have glass blowing as a hobby. So the original PhD student that was involved in building the atom probe, he's now retired. He was working at Los Alamos for a very long time, and his hobby was always glass blowing. There was his remnants from starting an atom probe, because that's when they originally built. They just glass blew all their own devices. And if you look at the emitter, it's a very simple model. So essentially we have a hemisphere on a cone. If you look at that in detail, it's not exactly true. You might be able to discern that there's some flatter parts and some rounder parts. So it's not exactly a hemisphere, but it's fairly close. And so that's a so-called tip on cone model. Tip on cone model. And that's not a bad model. And if you look at that, the question is then, what is the electrical field that you get? If you go into your physics books and you say, okay, I have a charged sphere. A charged sphere has a voltage V. Then the field on the surface, or the field at any radius r. So the field is voltage divided by radius r. And because we have this tip on cone, the field that we have equals voltage divided by some fudging factor times r. The question is where? Because of course you will have a different field here. You will have a different field here compared to here. So what we're talking about is essentially the field up here. But you will have some variation in field along the tip. The further you move down here, the smaller the field will become. But this is an approximation that's been serving us pretty well, even though we all know that there's a distribution in the field strength across the specimen. But as an estimate, we just take this approximation, and K is what we call the field factor. Field factor. Of course, these days, you could just set up a simulation and try to simulate that very easily, because nowadays our laptops are about as powerful as supercomputers were in the 70s, so it's not that big a deal anymore to try and simulate what the actual field distribution is. And I'm currently setting up a simulation like that in MATLAB, and I hope I'm going to be able to contribute it to the lecture before the end of it if I get to it. Okay, so that is a good approximation is something we can see here. This is from an old book, edited by some people that's still around. Richard Forbes I've only met very recently in Belgium, so he's still very much around. And you can see here we've just got ball on stick. Ball and sphere model. So just imagine we're taking a crystallographic arrangement, and we're putting a curve through it. And that's essentially what they had their students do. Just take a lot of, I think in this case it looks like marbles or I don't know, ball bearing balls or whatever, stack them on top of each other and make them into a sphere. And if you look at a field ion image, in this case of tungsten, I believe it would be, you see that it's very, very similar. It's very, very similar. And then you can have a qualified guess of what the crystallographic orientation is. So here we can see that it's arranged in different crystallographic directions. And I believe this would be different radii. So you can estimate from the distance between the terraces then roughly what the radius of your specimen would be. And of course, from the crystallographic features that appear, you can look at what crystallographic orientation that we have. And this is what I meant with, in the beginning, we can do some crystallography. Well, if we see an image like this, we can figure out what the crystallographic orientation is. And I'm trying to 3D print something like this right now, but my first attempt, which I wanted to bring to this lecture, unfortunately failed on Wednesday, so maybe next time, yeah? Maybe next time. Okay, so specimen preparation, very simple, electrolytic specimen preparation for specimens like the ones you saw up there. So there's essentially two techniques there, or three. You can just put a wire into an acid, and typically we do that in electropolishing, not in chemical polishing, so that we have some control over the removal, so you can switch on the removal and switch it off. Yeah? And typically what we do is we take the wire, we dip it into the acid, so this is the acid, or it can be a base. For example, if we have tungsten, we're using KOH, and here the acid we might have something like perchloric acid, HClO3. And in this case, this floats all on a liquid polymer. Liquid polymer, so Galdane is the one that we use. So you can just go and buy that, and it's an inert liquid, and that is heavier than these acids, so that if you do the thinning, a specimen gets thinner selectively here in the middle, where the acid is, and it doesn't edge where the polymer is. And so essentially, eventually it gets thin, so thin that it falls apart, and then when it does that, very often it's already thin enough to do atom probe on it. If it's not, what you can also do is you can not have the Galdane and just use a wire in an acid, and then it just becomes thinner on one side when you dip it in. Just works just as well. This is a very nice method. I have tried to motivate people here to use it a lot, but for some reason people still stick to that. But also we do a lot of FIP preparation, so people very often don't do electrolytic preparation to begin with. But we have everything here, so we have the liquid polymer here, for example, and of course the acid and everything else as well. But if we want to do that in a little bit more controlled way, what we very often do is the so-called micro loop technique. Micro loop technique. And what we do in this case is we create a loop out of a wire, and we suspend a droplet of acid in that loop, or base if it's KOH. And what we can then do is we can move a specimen in there, and you can see the specimen is crimped in this case in a copper tube, in some soft metal tube, so that we can hold it very easily, because here typically they are, let's say, somewhere between 0.2 to 1 millimeter in cross section. 0.2 to 1 millimeter in cross section, so they're a little bit hard to grip with your tweezers. And so very often we crimp them in a copper tube or a nickel tube or something like that. I also have gold tubes, but they need to come and ask me to use them because, of course, it's gold and it's expensive. But if the acid would create a problem with the copper, for example, then we can also use things like gold tubes. And then we do the same thing, just we can use a microscope to observe the electropolishing during the microscope. And very often what we do is we move the specimen back and forth, so that in an initial step, what we do is we create a specimen with a neck, and then we keep etching until the neck falls off, so that we have just a very fine tip. Because we do that in a controlled way on a microscope, we can actually make relatively sharp specimens that way. Of course, there's nothing modern about this. There's nothing modern about this. This is something you could have done 100 years ago. And people have, because the 30s are almost 100 years ago now. One thing we have done recently, maybe I'll show you in a video next week, is, I can have it on my phone also, I can show you later, is that we have made a computer-controlled version of this, so that the specimen always so that we always take a photo of the specimen after a certain amount of time so you can see a time lapse of the whole process, which makes everything a lot more controlled. But people these days use the FIB a lot more, so apart from us, not that many people care about electropolishing anymore. Okay, so the question is now, how does the whole process work? How does the whole field evaporation process work? Let me just keep time. Oh, half an hour. We got half an hour. How does the whole field evaporation process work? Yeah, because in principle, we're working on specimens that don't want to emit individual ions or individual atoms, just simply because otherwise there would be a gas. But we're working on solids. Solids don't want to, well, atoms don't want to naturally come out of solids, otherwise it wouldn't be a solid, because it would just be sublimating. And essentially what happens is that if you think of the bonding potential of an atom, so this here we have bonding potential U versus coordinate X, then a typical bonding potential of an atom looks like this. Lennard-Jones potential, you've seen a lot of those. And essentially we have an energy depth of a certain amount. That's the sublimation energy. That's the energy that the atom would need to overcome to evaporate. But if we put on a strong electric field, then we have a contribution of the field if we have an ion. So the potential, the bonding for an ion at zero field would look like something like the same as for an atom, but the energy would be higher. Because we need to put in the ionization energy. The ionization energy. But as soon as we start putting on an electric field, so if we put an electric field, then this energy gets modified. The energy of an atom doesn't get modified very much because it's not charged. If you have a field gradient, it would get modified a bit because, well, it's polarizable, but it's not charged per se. And if you do that by enough, we'll get a potential energy curve like this. And here you can already see, from this point here on, the energy of the ion would be lower than the energy of an atom. So if our atom for some reason would gain enough energy to move up to here, it would spontaneously ionize and fly away. And the good thing for us is we can change the size of that barrier, of this Qn. This barrier is Qn because we can change the field. So if we crank up the field, this barrier will get lower and lower and lower. And then the ion flux would be some kind of jump frequency. Times a Boltzmann term, times a Boltzmann term, which is just the probability to overcome this energy barrier. And the probability to overcome this energy barrier, which is of course temperature dependent, which is what we're using when we, for example, do laser atom probe, because in laser atom probe we change the temperature, and in voltage atom probe what we do is we change the barrier size. So this is through voltage pulsing, and standing voltage, the DC voltage, and this is laser. This is through laser pulsing. And if we do that, we can get, this is actually a video, but for some reason the video is not playing. Why is the video not playing? Pointer options. So if we continuously increase the field, and in this case the voltage, you will eventually see the atoms flying off. This is a movie from our colleagues in Rouen, and I think we should make our own movies because we can. And one thing you can see in this case is that if you look at where the field evaporation starts, this is continuously moving up the voltage. It starts at a very distinct voltage, which means this is a very controlled process, because if you decrease the evaporation barrier, eventually it will be overcome, and this is a very distinct point. This is a very distinct point. But you're going to be able to do that hopefully yourself after Christmas. And we do have a FIM already operating. We've worked on that and changed it around. So right now it's sitting in storage, but this is also being reactivated. And here on the top right, you see a field eye microscopy image of tungsten taking on our own FIM, which is exactly exactly that image, one of the images I was talking about that just one of our Heavies took with his phone. So you can just look at it and see that. Okay, so how do we get to the third dimension then? So right now we're talking about lateral distribution of atoms, and this is something that you can see very easily. So in this case we have X and Y. The reason why I put it in parentheses is of course because it's a curved surface that we're seeing. So it's kind of the coordinates that we get are kind of on a curved surface. And as we are removing more and more material, this surface moves down through the specimen. And this is actually a geometry that people already in the late 70s had pretty much figured out. So essentially, if you look at this, you can look at this as a stereographic projection of the surface. So if you look at here, this is a point at the surface, and the question for us is how does it translate onto the screen? And a relatively good approximation is that we have some projection point, which is not the radius, not the center of curvature, but some projection point. And if we look at if we connect those two positions, we can just look at the projection point and connect the two. In reality, it's not exactly how the ions fly, and the ions will fly outwards and then curve inwards. And that's got something to do with the fact that the detector is at a potential of roughly negative 3 keV. And we'll see later on why that is. This is why the ions fly in this light curve. Otherwise, if it's completely potential free, then they just get repelled a little bit from the fact that the field here points straight outwards and eventually points a little bit more towards the front. And this is also why there is some compression here as well. These two things contribute to what we call the image compression factor, and we'll talk about that later because that sort of determines the image that we get. And the reason, and this sort of gives us the ability to sort of this being our X and Y, but really a curved XY. So our coordinate system in 3D kind of looks like this is the number of atoms that we get, and then we have our curved X and our curved Y. And of course, we want to translate that into a real X, Y, and Z Cartesian coordinate system. And this is very often what we call the 3D reconstruction. 3D reconstruction, sorry, I ran out of space here. The 3D reconstruction, and this is a very important part of atom probe tomography. And we'll talk about that separately when we talk about data analysis. And that this very, very well reproduces already features is something you can see here. This is just me slapping one of those images, exactly this image, onto a hemisphere and having it rotate. And you can already see when things pass by that you can already see that atomic planes are reproduced accurately. to a very good extent. Very, very simple method. Of course, hinging on the fact that we have very nice field evaporation. Just imagine you have a very high bonding energy material next to a very low bonding energy material. Then your tip might not be looking as nicely, but it might look something like this. And then your ions here might be a little bit compressed, and here they might point a little bit outwards. And we'll talk about these artifacts or these situations in field evaporation later on. But if you have a very well-behaved system, in some areas you're even able to put atoms back on their place in 3D. So this is an example from the group in Rouen from a couple of years ago, where a PhD student did field ion microscopy in 3D, and then did analysis of essentially putting dots where the atoms are, and then also doing the progression in 3D. And he was able to, in certain volumes, position each individual atoms in 3D. And so this is essentially one of the few methods where you can do that. Nowadays, people also doing that in electron microscopy. But at the time, not that long ago, this was really only done in field ion microscopy. So remember, this is a technique that's now bordering on 80, 90 years, and is still producing useful new results. Okay, so this is just the thing that I explained before. So essentially, if we have an atom, then the atom's potential would roughly be this. If we have an ion, we need to put in the ionization energy. If it's a plus, then only once. But if it's a more than one plus, then we need to put in the energy more than once. So with different ionization energies. And if we add a field, in this case, a field of F, then the energy will be modified by n times the charge times the elementary charge times the field times the distance. Very basic physics, and this gives us this curve here, and this, where it crosses over with the atom, this gives us a residual barrier. This is a very, very simplified view of this, but unfortunately it's been very successful as a theory, even though that we know that from a quantum mechanical standpoint there's a lot of things here that can't quite be true. But only now, in the last 2 or 3 years, people have really been able to do quantum mechanics calculations. And maybe I'll pester the guys at Max Planck in Düsseldorf who have been doing these calculations to give me some nice movies. So now we're able to atomistically simulate these things as well. But the simple model is you have an atom that sits on a surface and it moves away from the surface. And that is a very controlled process. It's just shown here that this is from a colleague from Oak Ridge, Mike Miller. And what he did was just some field ion microscopy. And he just took an image of 9 atoms on a surface. 9 atoms on a surface. Then he increased the voltage, took another image. 8 atoms, increased the voltage, 7 atoms. And this is just going to show that this is completely manual operation. It is just a guy sitting there twisting on the knob, and then one atom comes off, take an image, another one comes off if it further increases, and so on and so forth. And again, I hope by the end of this lecture we're going to be able to do the same thing again, because our field ion microscopes hopefully work again by then. Also, yeah.
If we imagine this experiment and we repeat that again, the order which atoms get out of the sample are the same as we see here?
That is a very good question. Probably no, because there's a thermal activation part. So what will happen is that the ones at the edge, you can see they're a little bit brighter, right? Because they see more field. So the brightness, unfortunately, has not everything. To an extent, it has something to do with which atoms they are, but mostly how much field they see. So the ones at the corner, they see more field, and they will come off first. So the one in the middle will leave later, which is very important also for reconstruction. But if this is leaving first, or if this is leaving first, we can't really control. So this is the thermal part of the evaporation. And this is also something that we want to find out if there is some systematic to it, or if it's completely thermally random. Yeah. And I shouldn't have been drawing on top of that too much, because there's also a model about the below it. So can I get rid of the annotations? Under options, there is no clear pen. Or is there? Okay. So very often we observe also higher charged ions. So not just an iron plus, like for example a tungsten plus, but tungsten, we see tungsten plus, tungsten 2 plus, tungsten 3 plus, and even tungsten 4 plus. And the question is why? And the reason is when the atom is leaving the surface, so if it's moving from here to outwards, initially the higher charged atoms can't, the electrons can't tunnel into the solid because the Fermi level is all the way filled up. But eventually the ion is going to be far enough away, like here, so that the highest occupied orbital will eventually reach the Fermi level of the basic material. And once that's the case, as soon as it's a little bit further out, the energy will be positive and it can tunnel back into the solid. The question is how large the distance is. So if the distance is too large, then the tunneling probability will be very low. If the distance is very small, then the tunneling probability will be very high. And if you remember from the slides before, the distance, so the distance will essentially be dependent on the field that we have, and the field will be dependent on the temperature, because we get partially we overcome the barrier via thermal activation, and partially through reducing of the Q, through increasing the voltage. And so the higher the thermal contribution is, the lower the field is. So the lower this slope will be, because the slope here is elementary charge times field times distance. And if the field is lower, this will be further out. So lower field for the same material means higher temperature. And if you have higher temperature and lower field, then the distance will get longer and the tunneling probability will get smaller. So if we have higher temperature, either because we measure at higher temperature or because we use laser and high laser energy, then the lower the charge states we will see. Lower charge states we will see. Okay, so how did the systems work? So we'll just quickly go through that in the remaining couple of minutes. Well, this was the original one I already showed you, and essentially they just used an oscilloscope, and on the oscilloscope they just saw spikes when an ion arrived. And then they measured by hand essentially what the flight time was. Of course, we're talking about 2,000 atoms per second. You're not going to hand analyze 2,000 graphs per second. So this was more like 10 atoms per hour or 10 atoms per minute or whatever. And not this year, but next year we're going to have a detector and a scope to be able to do that by hand as well, so that you can feel the joy of doing that. Okay. And the pulses, so we have two types of pulses already mentioned, laser pulses and voltage pulses. And what I've talked about before is just drawn here. So this is the field, and this is the temperature. And from the simple equation that we had before as a linear approximation, the threshold field just goes down with temperature. And using voltage pulsing, we just go over the threshold for using the field. In laser pulsing, we just go temperature-wise. And this is a typical pulse. This is actually the pulse from the atom probe I'm going to show you downstairs. And you can see this here is about 1.5 nanoseconds, and the laser pulse would be roughly somewhere between, let's say, 400 femtoseconds to maybe 10 picoseconds, depending on what laser we use. Yeah, so on our LEAP atom probe that we have, it's a 10 picosecond laser as far as I know. On the OxCAD, so our home build instrument, we're going to get a roughly 400 femtosecond laser. And on the laser physics system that, for example, Mehrpart is using, we have a 10 femtosecond laser with around, with a pulse that's relevant, it's around 400 attoseconds. So there's plenty of room at the bottom still to go, but this is what's currently used, mostly femtoseconds up to picoseconds. And people haven't seen a lot of difference between sort of the couple hundred femtosecond to a couple of picoseconds regime. But this is something that we're currently still figuring out. Okay, so how does the time of flight mass spectrometry work then? Well, if you have a light atom, then it travels faster than a slow atom, and this is essentially the mass spectrometry. Here, for atom probe tomography, already including the aspect that an atom that flies up to here has a shorter distance to fly than one that flies up to here. This is also something we need to take into account. This is why for large detection angles, we need the spatial resolution, because otherwise we would start confusing atoms that just fly longer just because they're flying towards the outside of the detector, rather than the middle of the detector. And that's actually relatively easy to deduce. So essentially this is just the kinetic energy of an ion, and this is the energy that we put in. So this is the voltage that the specimen is at, the number of charges, and the elementary charge, because this is the amount of energy the ion gains. And typically, here what we assume is that we have a specimen and a field-free drift region. So that essentially the specimen is at a certain voltage, positive voltage, and the positive voltage is terminated at a certain point, close to the specimen. And then we have a region here where there is no field, and here we have the detector. In reality, most of the energy gain happens close to the specimen anyway, very close to the specimen. So we don't necessarily need this field termination. And in reality, most of the detectors are not at ground potential anyway, so we do have a field here. And this is something we need to calibrate out later on, typically. In the system we use at Laser Physics, for example, it's an electron spectrometer originally, and they've taken great care to actually have a field-free drift region because they work on low-energy electrons and they are heavily influenced by electric fields. And in this case, you essentially can take this equation, plunk it into your data, and it works straight away. No corrections needed. And from this, we can vary just with saying, okay, the velocity of the ion is just the flight time divided by flight path length. So this would be the flight path length, or actually this would be the flight path length, but we assume that this is very small compared to this. So small L is much larger than big L. And if we then just change that, then we will see that we have that our mass to charge. So this is the mass, and this is the charge state. Equals is proportional, so now this is including the K factor, is proportional to essentially the flight time squared divided by the flight path length squared. And we should maybe redo that actually properly next time, so that this doesn't confuse you as much. But the important thing is the flight time goes in square, which later is important when you see mass spectra, because what that means is that time bins at small mass to charges account for larger parts in flight times. So if you have maybe a hydrogen with a mass to charge of 1, then the area there counts from maybe 15 nanoseconds flight time to 100 nanoseconds flight time. Well, not that wide, but maybe from 50 to 55 nanoseconds. Whereas if you have a very heavy ion, you know, the time of flight for something like a tungsten might only be 1 nanosecond wide. And the reason why this is important is, that if you look into the mass spectra, and this is now in linear scale, very often we have logarithmic. In linear scale, you can see very little background, very clear signal. You will see that the background is larger here than here. The reason for that is simply that we have this square dependence. Okay, this is what the systems actually look like. I can show you downstairs. This is a delay line detector. This is one that we use. This is a stage that we've built. This is a commercial system, and there we only have sketches because it don't give you photos. For our own systems, we can look at the photos. And then if you do a nice reconstruction, you can even see the 3D distribution. This is one that I like very much. It's from the late 90s. So once people had built the first tomographic atom probe, they could, for example, show, okay, here we've got individual atomic planes, and if you count the planes here, you will see that there's one extra here because there's a dislocation. And from the flight line, you can identify, so this is in the third dimension, that you have a lot of boron atoms, in this case in aluminium, around at the end here, and this is a Cottrell cloud. So again, theory in the late 40s, measurement in the late 90s by atom probe. They were able to show that. Okay, and with that, we're at the end of today, and I'll keep the annotations and maybe put that online as well, and stop the